started. Thanks for you guys for being here on time. The topic today is energy. Energy is how scary a thing looks like. If a thing looks scary, it has a lot of energy. If you have a baseball flying towards you, it will look scary if it is really fast. It has some speed v, it's flying toward you, and you're scared. Now, when you are scared of the baseball, you are scared of its energy. You are not scared of its direction. You don't care if the baseball is flying from the left or from the right. They will be equally scary because you only care about how hurt it will be after the baseball hits you. You don't really care about direction. In Newtonian mechanics, we use F equals ma. That tells you everything. It's like a shotgun, kills everyone, but it's heavy. Sometimes we don't need to use a shotgun, and we don't need to use vectors. So there must be some way to make things easier, and that is energy. Energy is how scary this thing is. They are equally scary no matter which direction they come from, so you know energy should not have a direction. So when we talk about energy, we are talking about a number. For this ball, we use K because it has energy due to its motion, so we call it kinetic energy. Anyway, it's scary, it has energy. Now, if the baseball is flying slow, then you probably won't be that scared about it. So we know the bigger the speed, the bigger the energy. Okay? Now, the speed might not be the only thing you care, because if you have a slide ping pong ball flying equally fast at you, you might not be that scared of ping pong ball. You might not be that scared is because the mass of the ping pong ball is so much smaller than the mass of the baseball. When they are moving equally fast, they do not look equally scary because the mass of the ping pong ball is small and it doesn't hurt that much when it hits you. Therefore, we know that if the mass of the object is bigger, will the kinetic energy be bigger or smaller?
Bigger.
Good. So we know if there is something called kinetic energy, that the heavier and faster the object is, the bigger kinetic energy. Okay? And it doesn't matter which direction it's coming from. It's just a number. It's not a vector, so it should be easier. Now, a thing does not need to be moving to look scary. You can have a flower pot near the window of a tall building. And it looks scary from down here. It looks scary. Something is up there, and it's going to hurt you when it hits you. So we know the flower pot also has energy. It's not moving, but it still looks scary. So we call this kind of energy potential energy. We use U for potential energy. It's called potential energy because the position is high. That's why it has this energy. This energy is due to the position of the flower pot. But still, it looks scary, so it's energy. The higher the flower pot is, the more scary it looks. So we know if I say y is going up, then the higher the object is, will the potential energy be bigger or smaller? Bigger. Good, it should be bigger. Now again, the height is not the only thing affecting potential energy. If I am looking at the same tall window, but it's just a piece of leaf nearby that window, it is as high as that flower pot, but it doesn't look scary. It doesn't look scary is because despite how high its location is, the mass is small. So it looks less scary and the potential energy is small. Just like kinetic energy, the heavier the object is flying, the heavier the flying object is, the bigger the kinetic energy. The heavier the object is and the higher the object is, the higher its potential energy. Okay? Now, the reason that this flower pot looks scary is because when it falls down, it will hurt you when it hits you. When it falls down, it is moving after its position decreases. Up here, it's not moving, so we say the kinetic energy should be how big? How big should the kinetic energy of the object be if it is not moving?
0.
Good, it's 0. But now it is moving, so we know it has a big kinetic energy, or the kinetic energy of the flower increases when we fall down. And when you get down here, the height of its location is lower. It no longer has a high y position, so we know its potential energy decreases. So the reason that you'll be scared about something with high potential energy is because you can turn the potential energy into kinetic energy, and kinetic energy will hurt you. So that's why, even though the thing is not moving, you will still be scared of it if the potential energy is big. It can turn its potential energy into kinetic energy, and that's why it's scary. And we see that energy has different forms. They both look scary, they both have energy, but they can be scary for different reasons. One is because it is moving and it has a big mass. One is also because it has a big mass, but it is at a very high place. And you can convert different form of energy into each other. Here, the flower part converted its potential energy into kinetic energy, and then it will hurt when it hits you. Okay? So we say energy can have different form. It can be in a form of kinetic energy or in a form of potential energy. And they can convert into each other. Potential energy can turn into kinetic energy. But by how much? Should all the potential energy turn into kinetic energy successfully, or some of them will be lost, be destroyed, or just missing? Remember that we saw in Galileo's ring, if you release a ball from here, you release the ball from rest, so initially it's not moving. What is the kinetic energy in this state when you just release it?
Zero.
Good. It's not moving. If you release it from rest, so it's 0. So now we're going to use this subscript I to denote it is in the initial state. This I stands for initial. It's not the unit vector I. You can see it is not a unit vector because I don't put a hand and I squeeze it into the subscript. So it's just because I want to distinguish the kinetic energy in the initial state and the kinetic energy later. Once I release the ball will roll down. Initially, the potential energy is bigger, and as it rolls down, those potential energy turns into the kinetic energy of the ball. Just like the potential energy turns into the kinetic energy of the flower pot when you fall down, the potential energy of this ball turns into kinetic energy of the ball when it rolls down, and the ball is now moving with a bigger kinetic energy. So the problem is, does all the missing potential energy turns into kinetic energy or not? Remember that the ball will keep rolling, and once it starts rolling up onto the second rim, the speed will slow down, which means the kinetic energy decrease, but those will turn back into the potential energy because the height of the ball is rising up. And if you remember that it will reach the same height, then it means that the potential energy here, so this is the initial potential energy, this is the final potential energy. The ball has the same mass. The mass of the ball doesn't change. The height of the ball is the same in the initial and final state. So we know the final potential energy is the same as the initial potential energy. When you reach the highest point, the kinetic energy will be how big?
0.
Yeah, it's not moving. When it is at the highest point, there's a moment that the ball stops moving before it reverses. And at that moment, it's not moving, so kinetic energy is 0. So you see, energy can convert between different forms. It can go from potential to kinetic and kinetic back to potential. And when the energy are converting, all of them will be converted because you see the final potential energy you get back from the kinetic energy is the same as the initial. So none of the energy is lost, none of the energy is destroyed,